just show you how easy a lot of this is. So with the program open, I've got data sets on my desktop. Now the data sets were set up as SPSS files, but what's cool about JASP is I can click on that SPSS file and it comes up seamlessly. Now the thing you won't have is you're not going to have to flip between data view and variable view windows. But you know, in terms of what you have, it's going to, everything will be properly labeled. It'll pull things in with the correct labels. So I've got an example here where this is just a fictitious example where I've got people broken down into two categories, normal weight and overweight, and then that's going to be our grouping variable, our independent variable, and then the independent variable is going to be, and again, this is for illustration purposes, time spent eating Big Macs. Okay, so if I want to say, okay, is there a difference between the overweight group and the normal weight group, and how much time is spent eating Big Macs? So in other words, is working backwards on that, is the time spent eating Big Macs predict differences either being the overweight group or the normal weight group, or can you say that being normal weight versus overweight predicts how much time you spend eating Big Macs? Answer that either way. Pull the data up, and couldn't be simpler right here under common. Now again, you file, you know, what is it that you want to pull in? If you put it on the desktop, again, JASP is going to find it real, or you know, whatever directory you put it in, JASP will find it real easily if it is an SPSS or JASP file. Okay, so back to the analysis here. T-test. Now, independent or paired sample t-test. And the answer with this one should be independent sample t-test, because you've got two separate groups. You've got an overweight group and a normal weight group. So being in one group doesn't affect being in the other group. It isn't the same people twice. We're not looking at this like if we had some kind of a social unit where we have family members like parents and children or husbands and wives, we would expect some kind of influence. One would influence the other and could cause a correlation between the observations. Well, in this case, you know, we just have a random sample of overweight people and a random sample of normal weight people. Then we find some way to measure how much time they spend eating Big Macs. Okay. So t-test, independent samples t-test, drop that down. Now, what it's going to want here, it wants to know what your dependent variable is. So dependent variable, again, since with t-tests and ANOVA, our independent variables are going to be nominal. And what we have here is we have this specified as nominal, but we could just as easily change it to, I'm sorry, ordinal, but we could change it to nominal. For our interpretation here, it isn't going to matter because we just have the two levels. So weight is going to be our grouping variable. Okay? And then the amount of time. Okay? Time is a ratio variable. That is, you can have, there's a true zero there. We can say that somebody that spends 600 minutes spends twice as much time as 300 minutes. But for our purposes with the t-test, all it needs to be is at least interval or ratio. Interval ratio works too. So we're going to move that into the dependent variable. Now, some of the other things we have going on here. Well, we could have the effect size, location parameters. We could do descriptive plots. In this case, we really don't need them because the simple question here was whether or not there was a difference in the amount of time that overweight people versus normal weight people spent eating Big Macs. Well, if you can kind of read this, is a little bit small here, but so I can get that to, I'll just leave it as it is. We've got T equals negative 3.975, and probability of that being random fluctuation over here, 0.001. So 1 in 1,000 probability that this is just random fluctuation. Okay. So there's a difference here. Okay, let's see if we can get some more numbers out of this. Okay, so let's say instead of just having that, I want descriptives. Because all the t-test tells me is that there's a difference between those two groups, and that difference, the probability of that difference is just random fluctuation, is 1 in 1,000. So I go for the descriptive statistics here. I guess I'll have to repopulate that. So dependent variable time, weight, grouping variable, and here's our descriptive statistics down here. So it gives you, in the example here, we have 10 people in the overweight group and 30 people in the normal weight group. So unbalanced cell sizes, but with independent sample t-test that could happen. Now, the time spent eating a Big Mac. So the mean for the overweight people is 589. The mean for the normal weight people is 698.4. So the conclusion here is that you have a significant difference between these two groups. And the interpretation is, since 695 is greater than 589, the normal weight group spends more time eating a Big Mac. Okay. Now, what that ultimately means, that depends on what your experimental question is, but the conclusion here is that within this sample, the normal weight people are slower eaters than the overweight people. Now, I don't know if that has anything to do with what's out there research-wise or anything else. This was an example that I got out of a textbook. Now, let's do another type of study. Open, tell it to go to the desktop, and as you can see, I have tons of data here. And we won't look at the students' GPA. Let's look at this one here, cold symptoms. Okay, so it's going to open up another window and give you the setup on this. What we have here is a study where people were studied over 2 years, and they were asked to record the number of days with cold symptoms for year 1, and then for year 2, record the same thing. And our independent variable here, this difference variable, what that's going to be is it's going to be the difference in the number of days with cold symptoms, year 1 versus year 2. So in other words, if we're going to say, okay, somebody had 10 days with cold symptoms in year 1 and 18 in year 2, then that's going to be 2, because it's going to be 2 less days that they spent with cold symptoms. On the other hand, if that's a negative number, so for example, they reported 10 days with cold symptoms in year 1 and then 20 in year 2, that's going to be negative 10. So they actually spent more time with cold symptoms that second year. Now, to make this a little bit more interesting, what we're going to do is we have people put in 10 groups, whether they got a placebo, whether they got a low dose of vitamin C, or they got a high dose of vitamin C. So one hypothesis here is that vitamin C reduces the number of days one would have cold symptoms. That was something that people kind of believed in since the 60s. Okay. Be realistic with this. The studies tend to be a little bit mixed with results, but I set this one up just for illustration purposes. Okay, so I've got 3 groups here. My independent variable is going to be the number of days with cold symptoms between year 1 and 2. Was it more or was it less? And then I have the independent variable, 1 by 3. So treatment, whether it was a placebo, low dose of vitamin C, high dose of vitamin C. Again, we could expand this and we could say, okay, if we would gather information in terms of whether these were men or women, we could add another variable to that. We could have a 2 by 3. We could have male and female by placebo, low dose of vitamin C, high dose of vitamin C. Okay, so to ANOVA. Click on ANOVA. And again, like with the t-test window, okay, our dependent variable is going to be a scale variable. So we're going to move cold symptoms, or the difference in days, the dependent variable, and then the group, placebo, low dose vitamin C, high dose vitamin C. We're going to move that to our fixed factors. Okay. Now, again, what happens with JASP is you don't have to hit submit or wait. We get the information right away. But and what we have going on here is, looking at this, we can see that there's a difference among the 3 groups. So that F ratio comes up as being significant. It's this number right here, that F 4.836, significant at 0.016. 0.016 is less than 0.05, so it's significant below 0.5. Now, some of the other things we want to take a look at. Model, Well, we don't really have to do anything with this. The default is type 3 sums of squares, which is the sums of squares we've been talking about in class with respect to calculating the degrees of freedom. Post hoc tests could be kind of interesting. So, and we previously talked about the two tests that I typically use, Tukey's and Chaffee's. Chaffee's being the more conservative test. So you click on that post hoc test, correction, and what that refers to is correction for type 1 error, with the Chaffee's test being the one that's going to be the most stringent. Now, again, Tukey's is kind of a medium duty. It's sort of a less conservative test. Because I do a lot of stuff in applied settings, I usually default to a Chaffee's test, because Chaffee's test tends to be really fairly conservative. Actually, out of the options, it's usually the most conservative test we have. I'm going to click on effect size too, because that tells us not only was there a difference there, but how big was that difference. So I add that. And then the other thing I want to take a look at here, descriptives. Okay. So group. Now I'm only going to have one line here. That is, I'm going to plot the means for days with days with cold symptoms compared year 1 to year 2. Okay. So what I have here, this is placebo group, low dose of vitamin C, high dose of vitamin C. They still need to work on getting the graphics to work. But if you go to print this, it will actually correct it. It goes to print. Well, anyway, back up to the top, what I have here. Significant difference between the three groups. That's what the F ratio tells us. But what it doesn't tell us at this point is which group is different from which other group. Okay. So we go down here to the post hoc test. So what's happening here is it's comparing placebo to low dose vitamin C, placebo to high dose vitamin C, and then low dose to high dose vitamin C. Now, if you do this in SPSS, it's going to give you every combination of those variables, starting with one of them, the first place, and then subtracting the others. What happens in JASP is it basically just gives you all the differences here. So there's only 3 comparisons there. They're stated right here. So placebo, low dose, placebo, high dose, and then low dose, high dose. Okay. Then over here, T statistics, Cohen's D's. The Cohen's D's are the effect size. And if you look at what we have here, we have a kind of a low effect size, but it comes up as being kind of important. Now here with the Tukey's test or the Chaffee's test, this is telling you at what probability level the difference between placebo and low dose vitamin C and placebo and high dose vitamin C were different. And over here, 0.038, 0.038 with the most conservative test, it still comes up as statistically significant. If you back up over here with the Tukey test shows a much lower probability level. And again, this kind of illustrates the idea that the Tukey's test is less conservative than the Chaffee's test. Likewise, comparing placebo to high dose vitamin C, the Chaffee's test comes up at 0.042, the Tukey's at 0.033. So again, Chaffee's test is more conservative. When if let's say it's more important to not make a type 1 error, to not have a false positive, that's when you go to the Chaffee's test. Again, my reason for using it is you don't control as much stuff when you're doing quasi-experimental research, when you're going to workplace settings. So if you're going to conclude something that could cause an organization to change their business practices, models, how they work with their employees or whatever, you want to probably err on the side of caution if it's going to end up costing money. Down here, low dose versus high dose vitamin C, no difference here. Okay. 0.999, 0.999, regardless of whether it's Tukey's or Chaffee's. And you kind of see that illustrated down here too, that here's low dose and here's high dose vitamin C. So the interpretation here was with respect to this population, it didn't matter if it was high dose or low dose vitamin C. The participants reported significantly fewer cold days than if they had had the placebo. So the mean difference here, this is literally the difference on average from the placebo versus the low dose vitamin C. Now, for this to be a positive number, what has to happen is that this one has to be smaller than this one. So looking at this data, about 5.6 or 5.5 days, actually slightly higher mean difference with the low-dose vitamin C, but not a difference that can't be explained by random fluctuation. So the conclusion here is that, generally speaking, the vitamin C is going to make a difference either at the high dose or the low dose. Okay. Let's do one more of these. I'll give you something that approximates the out-of-class activity for tonight. I'm going to go back to File, go to Desktop, and the data file I'm going to use now is this is going to be self-confidence by life domains. So we're asking a participant group how confident they feel, and the idea here is self-confident in intimate relationships, self-confident in friend relationships, self-confident generally or in common across all situations, common in common sense reasoning, confidence in academic settings, and then confident in how they conduct their lives. So this is something that can be right out of social psychology. Okay. Now, I said this was going to kind of resemble the out-of-class activity tonight. So what we're going to do is we're going to see if there's a correlation. Do people feel confident? We say, okay, we build a case that people that are confident generally feel confident across all different areas of life, or do people feel confident in certain areas but not in others? So we'll go to regression, and we'll just do a simple correlation matrix. Now, in the upcoming classes, we'll talk about other ways to try to analyze this. There'll be ways where we can say, okay, X amount of the confidence is coming from intimate relationships, X amount of the confidence is coming from academic relationships, things like that. Now, what we have with respect to our variables is we got 5 rulers here. Okay, so what we're going to do is we're going to highlight all those. We'll move them over to the variables box. Now, we have checked here is we have Pearson. So Pearson product moment correlation, since all our variables are either interval or scale, this will work. However, if you clicked on Spearman or Kendall's tau, chances are with most statistics packages, the computational formulas are going to be the same. So what's going to happen is that your output is going to look the same. Okay. So if we look at what we have here, this is correlating each one of those different areas, the confidence ratings from each one of those different areas with each other. Now, what we don't have here is we don't have to, if we've done the correlation once, we don't have to repeat it. And of course, the part right here in the diagonal, which is called the diagonal, everything correlates 1.0 with itself, so we don't need numbers here. But, looking at this, people that, how much is correlating confidence with friends correlate with intimate relationships? Well, that's a fairly decent correlation, but it's not super high, right? So it isn't like those are going to be identical, but they're going to be fairly strong. Common with intimate doesn't correlate that much. Academic with intimate, look at it, it's kind of not only is it small, but it's non-significant down here. So underneath, here's your correlation coefficient. 1 to 3 is a small correlation, 3 to 6 is a medium correlation, 6 and above is a strong correlation. So we got a medium correlation here and significant people's points are 1. So 1 in 1,000 that those two are just associated. That's just random association. Well, it's not, right? It's less than 0.05. Same thing with common and intimate. Okay, 0.01. But academic and intimate, there's no correlation there. So one doesn't, your confidence in your academic confidence in academic settings doesn't correlate with your confidence in intimate relationships, according to this data. And then general and intimate. Well, moderate correlation there, something a little bit more, something that is definitely statistically significant. Now, if we go over to common and friend relationships, moderate correlation, it's significant. Academic and friend correlates a little bit, okay? So kind of a small correlation there, 0.244, and it's below 0.05, so it is statistically significant. Okay? And then general and friend, and of course, significant, but moderate correlation. Now, common and academic, Moderate correlation, significant at 0.01. Common and general, moderate correlation, 0.01. Now, academic and general, small correlation is below 0.3, and it's statistically significant. So how do you interpret this? And, this one, you can take a look at those patterns and you can state whatever, what you think those indicate. My takeaway on this is that the one you can say that doesn't correlate is academic and intimate relationships. The confidence you feel in those two relationships don't correlate. Everything else seems to correlate somewhere between small and moderate. The one that tends to be the single best predictor here, general and friend. So general confidence, generally speaking, how your confidence and how confident you feel with friends correlates, kind of on the high side of moderate. Same thing with friend and intimate. Now, to interpret any of this, to say that, okay, how much of the difference does your confidence you feel in friend situations correlate with intimate relationships, or how much of the confidence you feel in general correlates with friend? Take that and square that correlation coefficient and multiply it by 100. So in other words, if something is 0.5, square that. 0.5 squared is going to equal 0.25, and multiply that by 100, so 25%. So where this gets kind of interesting is it kind of says that there isn't a general pattern, or there isn't like a general confidence that people feel, at least if this data is correct, there's a general confidence that people feel across all situations. However, there's a little bit of overlap among some of these. Now, where we're going to go with this in the weeks to come is we're going to take a look at this and do something called multiple correlation, and just see if what we'll do is we'll take a look and see which ones are more separate from the other, and which of these share or where the variance really overlaps in some kind of meaningful way. So I'm going to stop right there for tonight. I hope some of this is helpful. I'm going to be posting more of these as we roll into the floor.